All right, so the central limit theorem is an important backbone of statistical and econometric theory, right? It says that if we take samples selected from any population, the sampling distribution of all those sample means will approximate a normal distribution. And this approximation increases and improves with larger samples. And so we can use the central limit theorem when one of these two things is true. We know that the population is normal, or we have a sample size that's greater than 30. So if the population is normal or symmetrical, you're going to see a normal shape of the distribution emerge with samples as small as 10. So let's get rid of normal because your book does say symmetrical, but for these purposes, it's kind of like when we do the Kahoot later, it'll say normal. It'll talk about the population has to be normal or the sample size is greater than 30. But let's stick to what your book is saying. So when the population is symmetrical, you still have a sample size limit. Your n has to be greater than 10. So this is one of the more useful conclusions. It's true of all population distributions and allows us to use the normal probability distribution for confidence intervals, which we're going to do in chapter 9. So the central limit theorem, take a look at, I'm not going to reproduce it because it's going to be terrible, but take a look at chart 8-3, which shows this central limit theorem in action. Now, what are some of the conclusions that we have of the central limit theorem? Well, we know that the mean of the distribution of sample means is going to equal the mean of the population exactly if we select all possible samples of same size from the population. We talked about how the spread of the distribution of sample means is going to be different than the spread of the population parameters. And so the kind of corollary to that is that we have a new standard error formula. Really of the sample means, right? So this is going to be of x bar. So now we're going to take whatever that population standard deviation is, and we're going to divide it by the square root of n. So as n gets larger, the standard error becomes smaller. It's going to be less dispersion of the sampling distribution of the sample mean than in the population. So this is to reflect Gesundheit. So the reason why this guy is here is to reflect the fact that there's less dispersion in sampling distribution of the sample means. And so that's why this number is going to be smaller than just that population standard deviation, to reflect the less dispersion that we saw in that previous example. Questions on central limit theorem and the conclusions of it. So as long as we select all possible samples, the average of our averages is going to give us the true population mean.
Are we going to be using central limit theorem in order to apply stuff like the empirical rule to samples of populations?
Mm-hmm.
Okay.
Yep. Yep. We will get there.